So I'm Jay. I'm going to talk about some of the work that we've been doing over the past couple of years at the University of South Carolina, looking towards developing bifunctional catalysts, catalysts that will allow us to contain two functionalities and be able to all right, we're good. In any event, we're looking to develop bifunctional catalysts to convert biomass waste, things that we wouldn't use ordinarily, into biodiesel. Now, the reason, the sort of motivation for biodiesel in general is the fact that it's something that nominally could be considered as being almost CO2 neutral. It's something that's going to take the carbon dioxide that's already present in the air, convert that into oxygen and into carbohydrates, and then convert back into hydrocarbon fuels, burn and grab again. Unfortunately, no clicker. Oh, fantastic. Thank you. This is much more I'm sorry. Maybe I should just be confined. Is this not going? Is that the HDMI port? That's the HDMI port, isn't it? I apologize. So in any event, where are you? Clicker, that's laser. There's a laser. Good. We have to consider this from a historical context, right? We want to convert biofuels and biomass into sort of solve-all. People would prefer it to be a catch-all, something that's the golden bullet that's going to solve all of our energy problems. And one would think that this sort of trails back to our idea in the 1800s, almost all of our energy, all of the energy that we generated came from biomass, the burning of wood, the burning of peat, moss, and so forth. And then around the Industrial Revolution, we had this sort of conversion into coal, and then finally into oil, natural gas, and I love other renewables way up there at the top of the graph. Current day accounting for about 5 to 10% of total energy generation. The problem is that this is normalized to the amount of energy that we're actually consuming per year. So although this graph looks nice and flat, if we consider the total amount of energy generated, it goes off of the scale. Keep talking. It goes off of the scale pretty rapidly, particularly around the turn of the century, the 1900s. So if we want to be able, right now biomass globally accounts for something in the area of 10% of our total energy consumption. This includes energy for fuel, this concerns heat, particularly the burning of coal, not coal, wood. This is not disconcerting at all. Completely calm. So we want to be able to displace one of these. Particularly, we're going to target oil. And in the U.S., this makes sense. Now, it doesn't work. Goes backwards, forward. We have to consider things realistic, right? We can't just say that we're going to create biofuels and they're going to fuel every car in the Union because we don't have the resources. Even in the U.S., with as much land mass as we have, there is not enough land mass to make enough switchgrass to be able to completely displace gasoline and diesel fuel. This is from the National Renewable Energy Lab's GIS survey. This basically used geographical information to be able to look down and estimate how much arable land there is present in the U.S. that we could then use to convert into biomass. So we use power, right? We can produce 62 gigawatts of biomass using the entire continental United States. This accounts for roughly about 10% of our total energy consumption. So we're never going to be able to use biomass to replace coal, to replace natural gas, to replace petroleum. We're going to need to select niche applications, and in particular, long-range trucks, ships, planes. These are things that we could actually reasonably use biodiesel in. In fact, there was just, I think, 2 years ago, the Navy demonstrated the so-called Great Green Fleet. Has anyone heard of this? So they powered their entire sub-portion of a couple of aircraft carriers and destroyers using only biodiesel. Now, the cost was about 6 times what it would have cost to use regular diesel, but that's more a process of scale. So what are the state-of-the-art techniques? We want to make biodiesel from something that we can't use, hemicellulosic biomass, and we want to create linear hydrocarbons. There's basically 3 methods in which people use to do this right now. First method is through just rampant gasification. Let's take every CC bond, every CH bond, We're going to break them at high temperatures, split them up, get them into carbon monoxide and hydrogen, and then we're going to use something we understand. We're going to use Fischer-Tropsch synthesis to make diesel fuel. This is a proven technology. Germany, for instance, in World War II, ran their entire army and military off of syngas to create diesel fuel. Likewise, South Africa makes most of their diesel fuel through Fischer-Tropsch. However, you take a huge energy efficiency loss. And you can understand it. You're breaking every CC and every CH bond, making carbon monoxide in a partial oxidation, and then rebuilding it step by step to form diesel. Likewise, you can take it up to very high temperature using pyrolysis. This is a good way of getting at bio-oils, acids, alcohols, esters, and then you can convert those into a biodiesel. Again, it's a liquid fuel, but your overall energy efficiency is only on the order of 40 to 55%. A much more better method, wow, that got loud quickly, would be the use of hydrolysis. So this is a much more mild technology. You basically sit it in a beaker, and you can do it in batch, or you can do it in continuous plug flow reactor. You do it at reasonable temperatures, and you can get bio-derived chemicals, sugars, in particular furan. The advantage of this is that your energy efficiency is boosted by almost a factor of 2. You're 70 to 80% efficient in your production of biofuel. So we're actually going to target this in our study. And in particular, we're going to use 2-methylfuran and butanol as our potential feedstocks. 2-MF is readily obtained from furfural, in particular when you're making, let me check the name of that acid. When you're making furfural acetylene, when you're making one of the furfural derivatives, you can make it either at about 180 degrees C, or if you increase the temperature to 250 degrees C, you can produce pretty much exclusively 2-MF. When these two are in placement with one another, around 60 to 70 degrees C, they can undergo acid hydroalkylation. First, basically kicking off that CO, making an OH, and then bonding to one of the 2-methylfurans. You also have the possibility, if you have enough of the 2-MF present, to undergo a second acid alkylation, form this 1,1-bisyl vinyl butane. And then afterwards, you can do, on a separate catalyst, for instance, platinum carbon, a hydrodeoxygenation and then get linear hydrocarbons. Furfural, again, is nice. A lot of the people in the biomass community are targeting this because it's a relatively easy, straightforward thing to get to from hemicellulosic biomass. You can also go through levulinic acid. So the recent work that we've been looking at is this paper from Corman on Gewandte Chemie a couple of years ago. Very simple idea, very nice. They take 2-MF and butanol, they put it in the presence of toluene sulfonic acid in order to do the hydroxyl alkylation. Inside of the same doer, they basically can get a second use out of the toluene sulfonic acid to make a second alkylation to get this 1,1-bisyl butane. I'm an inorganic material scientist. They can and then they actually have to do a second step now. They have to do a physical separation, separate the water from the oil on top of it, and then do a second at high temperature hydrodeoxygenation using a platinum carbon support, or platinum on carbon support to get their eventual 6-alkylene decane. It's a pretty good work. I mean, they get about 87% yield, but since they're using a liquid acid, we have a number of that will work. Problems. First of all, it's a non-continuous. You have to do several unit operations. They're all batch reactions, and in between you have to do separations, which cost you extra energy. After this step, you actually have to pull this off of the top of the sulfonic acid and the water, and then place it back into another reactor. That makes for a very complicated operation, and you've also got this liquid acid that you've got to eventually dispose of. The idea then, is pretty straightforward, is why don't we use a solid acid in place of this? Now, since we're now going to the use of a solid acid, we can use that solid acid as a support. So now we can combine simultaneously the acid, the alkylation, right, along with the hydrodeoxygenation functionality in a single catalyst. And then in one step, we can go from here to here. We can get higher production rate, and now we can put it in a plug flow reactor. We don't need to worry about separation. Separations can happen down the line, particularly during the condensation step. We'll get high energy efficiency, very easy operation, and we don't have to worry about what we're going to do with the liquid acid when we're done. We do high throughput in my lab. We are combinatorial material scientists, and the first thing that we want to check, since we're looking for bifunctionality, is we want to look at our solid acid, our support. How functional is that going to be? So very simple batch reaction. We set up 6 of them sitting parallel to one another. Everything's done at a bar, very low temperature for 16 hours, use a relatively small amount of catalyst and product, and we just stir, and we see what's happening. First thing we want to look at is ZSM5. We've had a tremendous amount of success, particularly doing hydrogen cracking reactions of hydrocarbons, heavy hydrocarbon fuels, particularly JP8. And this got nice acidity to it. Unfortunately, it has very poor conversion for this particular reaction. We thought that most likely the issue was the pore size. The pore size for ZSM is somewhere in the area of 5.4 to 5.6 angstroms. And this 2MF is just too huge for that. It's 5.72 to 7.21 angstroms, depending on how you sit it on its edge. So the next step is to do mesoporous ZSM. And we got a 600% increase in selectivity, or conversion, but unfortunately it's still only 6%. So from there we moved to a mesoporous zeolitic system, in particular looking at MCM41, sulfated zirconia, and amberless 15. And we were able to substantially increase the selectivity to our intermediate step. Issue with amberless, however, is that it's only stable up to about 150 degrees C, and we want to do this at high temperature. We're doing the hydrodeoxygenation. We're going to use platinum and nickel, so we're going to need to be up around 250, 300 degrees C. The amberless is going to degrade. Likewise, if anyone's familiar with the petroleum industry, we spend a lot of effort doing hydrodesulfurization, getting sulfur out of petroleum. So we don't want to use something like sulfated zirconia in the end if we can avoid it. As such, we chose to go on with MCM41. MCM41 is fantastic. It's got this wonderful pore structure. Pores are typically anywhere between 25 30 angstrom. That's more than sufficient to get the 2MF in. Likewise, it's got a relatively high surface area, about 1,000 meters squared per gram. Next step, though, is to impregnate the platinum into the MCM41. And first of all, to make sure that the platinum is near our active sites. So we do wet impregnation of the platinum. We calcinate at high temperature. First thing you got to check is to make sure that the mesoporous MCM41 survived the calcination. So here's the XRD fraction pattern. We see that we get the nice peaks here indicating that we've preserved the pore structure of the MCM41. Likewise, if we look at the TEM, we can see that although we do have some blobs of platinum, which are most likely sitting on the surface of the MCM41, we seem to have pretty substantial incorporation, elongation of the platinum nanoparticles, which would indicate that they're actually being incorporated into the MCM41 channel, and therefore are going to be necessarily located nicely next to the Lewis and Bronsted acid sites in the MCM41. Unfortunately, while the pore size doesn't change all that much once we've impregnated the MCM with platinum, it's still around 3 or 30 angstroms. We take about a 30% hit in the amount of surface area, amount of active sites that we have available from the MCM41 once we've impregnated the platinum. It's understandable. Yeah, we've taken platinum, we've plugged it into the channels. If I have one platinum on one side and one platinum on the other, or a crush pore, then I'm no longer going to have access to the MCM contained between them. But we still have 70% of the overall surface area, which means catalytically we're going to be still relatively active. We're not doing ion exchange. The platinum is going in and it's basically maintaining its metallic state. So we have platinum nanoparticles incorporated within the MCM41. And so this is our idea. This is conceptually what this looks like. So we have our MCM41, which forms these nice long channels. We're going to incorporate the 2-methylfuran and the butanal. They'll go in, they'll do their initial hydroalkylation. They'll form our intermediate product. They'll eventually percolate down to the platinum where they'll combine with hydrogen, give us our undecane. Mission accomplished. We can't do this at ambient pressure. We can't do this at room temperature. We're doing this in a plug flow reactor. We're pumping in 2MF and butanal using an HPLC, introducing hydrogen using a mass flow controller. The entire thing is done at 40 bar. We first reduce the platinum, if that can be done, at 400 degrees C for an hour, after which we run our reaction at 350 degrees C for 20 hours. Gas hourly space velocity is 6,000 inverse hours. So using just the platinum, 0.1 weight percent platinum on MCM41, we have a conversion to linear hydrocarbons greater than 90%. Our selectivity is C9 plus is better than 75%, or around 75%. If we switch from platinum, which is a noble metal, to a transition metal, which will have issues with carbon formation, if we go at very high temperature, for instance, nickel, increase the loading, we still get a high conversion of around 90%, but our selectivity ticks up slightly to around 82%. But what's the other 25 and 18%? Mostly of what we're forming is C9 plus, around 75 and 82%, as I mentioned. But the platinum seems to have a slightly stronger preference for forming C5 and C4. This means that we're having direct hydrodeoxygenation or hydrogenation of the butanal and the 2MF at the platinum. They're not having a chance to react with one another. They're getting on the catalyst, immediately doing their hydrogenation, and they're done and they're out of the reaction. This is less of a problem on the nickel, where we only have about 18%, basically 9 and 9%, which is not terribly fantastic. Oh, no, it's actually great. But we have to understand how this is happening. We have to understand the reaction pathway that they're undergoing. I mean, what I'm proposing is that I have the 2MF, the butanal, they alkylate, and then we hydrodeoxygenate them to form our own decking. Alternative pathways, since we have so much hydrogen and we have the HDO catalyst present, is that we could actually have the 2MF and butanal either together, hydrogenate and then combine, or separately, one then the other. So one of the ways that one can test this is one can look at these intermediate species and run them through our batch reactor and see if we can get any conversion. And in this particular instance, the 2MF and butanal still give us about 62% conversion. The hydrogenated versions, butanol or the 2MF that's been hydrogenated, do not show any conversion. So this gives us a hint that most likely route 1 is the method by which we're actually forming our biodiesel. To further confirm this, we can just run the reactions in the presence of hydrogen or an argon. If mechanism 1 is correct, then these two are going to combine with one another. They'll form our intermediate and go to the undecane. If mechanism number 2 is right, as long as I'm in hydrogen, I'm going to have very high conversion. But once I go into argon at 7 bar, this reaction will no longer function. And as you can see, there seems to be some contribution. There does seem to be a non-negligible amount of the butanol or the 2MF that are hydrogenating, but primarily this is happening through a direct reaction of the 2MF and the butanol. We also have done a fair amount of spectroscopy, in particular looking at the formation of these OH stretches in FTIR. So this is an indication that we've reached this intermediate species. As long as we're running in the carrier gas like helium, the presence of these OH stretches indicates that we're not getting, in fact, this hydrogenation is not responsible for the formation of this eventual intermediate product. Wouldn't it be nice if we didn't have to start with 2MF and levulinic acid or butanol materials that 5 minutes with all of the craziness? Awesome. So what we've been pushing towards over the past year is 2MF is a derivative of furfural. Butanol is related to levulinic acid, but it's a little bit easier to work with. It would be nice if we could push back to our feed product, our feedstock, to an earlier derivative, something that doesn't require quite as many chemical reactions. So this paper by Jesse Bond from Domestic Group got us thinking about this. This is, again, a very complicated process for taking gamma-valerolactone to form Ca+. I mean, you have to do an initial reaction to get down to butene. Then you've got to do a separation, get the water out, take your butene and CO2, oligomerize, right? Then do a second separation, forming more CO2 until you finally get your diesel fuel. We're basically doing these reactions already. We have a catalyst that does this. So the question is, can we go even farther back? Can we start with levulinic acid? Can we do our hydrogenation, decarboxylation? We're still going to have to do a separation, possibly. Oligomerize, and then get to liquid fuels with comparable conversion. We want to be able to convert it around 75%. And we want to do this all in one step. Now, for this particular process, we're going to include butanal. Butanal, we found, is a wonderful linear hydrocarbon for these types of reactions. The hydroalkylation loves it. And we found actually on platinum ZSM5, we are able to switch now to the smaller pored ZSM5 because we're using 2 linear hydrocarbons. We're no longer trying to put 2MF and squeeze it into a small micropore. We actually get conversion about 42%, and preliminarily, we're already seeing a selectivity in the area to C9+ of around 42%. So this is something that we're very actively pursuing. In fact, we were looking for a time to do furfural. Furfural is tricky. It likes to make humans, and not the type that run around and yell at you because your microphone doesn't work, with an I instead of an A. So we've actually discontinued that particular aspect of the work. Furfural and this, using hydrodeoxygenation and alkylation, doesn't function the way it should. Again, our conversion's pretty high. We get 42 to C9+, and most of what we're getting is around a C5+, which is telling us that we're doing basically a direct hydrogenation of our butanal. So I wanted to take a minute and talk a little bit about the Materials Genome Initiative, and in particular, how it pertains to catalysis. I assume that you're all familiar with this. This was announced by the White House in 2011. The whole idea is to take the time from the initial identification and discovery of new materials out to final commercialization, down from the established 10 to 20 years, down to something on the order of 2 or 3 years. This is happening. I can't emphasize enough. Dow Chemical is massively invested in the use of MGI, and in particular, the experimental aspect of it, high throughput experimentation. Infuse, the recent diblock copolymer, non-randomly but ordered diblock copolymer developed by Dow, was developed using MGI. The current generation of turbine blades from GE was developed using MGI/ICME, where they wanted to replace rhenium with osmium. This is in the process of happening, and it only happens when we live at this intersection that exists between the new advanced computational tools, be they fluid dynamics, be they density functional theory, be they Monte Carlo simulations, experimental tools, in particular experimental tools that allow one to rapidly validate and discover new materials based off of theoretical hits, and the rigorous archiving and data mining of large base data sets. This is something that neither group, the computational folks, are a little bit farther ahead of us than the experimentalists, I would say. Right now, there are things like SunCat, Materials Project, AFlowLib that contain large archives of inorganic materials, database properties created through density functional theory. This doesn't exist for catalysis in an experimental standpoint, and this is something that's really lacking. But once you can integrate these three into cognitive workflows, you can create this materials continuum where data and information flow between each of the individual sets, and you can rapidly expedite the rate at which new materials are discovered. High throughput combinatorial processing is sort of the experimental benchmark by which this is done. We held a workshop in San Francisco this past May. I helped organize it with the White House Office of Science and Technology Policy. It was sponsored by NSF, NIST, and co-organized by Applied Materials. And the idea is that we need to create, in the catalysis community, an understanding of high throughput material science and a set of experimental tools that are standardized across the community that would allow for the free dissemination of information between groups. To take somebody like at JCAT that's working on CO2 hydrogenation to make methanol or to make methane, and somebody that's perhaps working at BASF looking at ammonia, SCR catalysts, and to be able to create a pathway by which they can exchange information about basic fundamental materials properties. Am I over my time? I got about a couple of minutes? Okay, cool. So we're in the process of establishing this in the inorganic materials community. JCAT, which is the Joint Center for Artificial Photosynthesis, is a very heavily catalysis-oriented group. We have at this point at SLAC high throughput in situ synchrotron microdiffraction system that allows one to take, we're at the point right now where we can acquire 50,000 different diffractograms in situ along with XRF per day. We're in talks right now in particular, because this is the interest of JCAP and my own group, with incorporating this with XAFs and Zane so that we can look at local coordination of metals, particularly during catalyst synthesis or under catalytic reaction conditions. And I asked this question of a gentleman that came before me, and I don't have a good answer for this, is how do we handle all of this data? How do we systematically go through such a large and sometimes rather unformatted set of data and generate not just knowledge about a particular project that I'm working on, yay, biofuels, but how do we use that to inform people who are working on CO2 or looking at methane activation? This is an open question in the field. I've gone over my time, I apologize. We do bifunctional catalysts. We take 2MF, which is a biomass-derived platform chemical, to diesel. We make a good portion of C9 and C10 from it. Basically, it works in one step, and we think that we can take this and we can apply it to levulinic acid, not so much furfural, butanol, and other biomass-based chemicals. Thank you for your attention and your patience.
All right. Now, this is actually our last speaker for the day, so we can take a couple of questions. If anybody has any questions at this time. Okay, we got a question right over here.
I didn't see the analysis of C9 compound is made of completely linear or isomeric compound.
We have both linear and branch chains. We have a mixture of the two.
And so the question is, what kind of octane number is that? If you're going to substitute the gasoline, and then what is the octane number of that fuel? Do you know that?
No, that is something that we're actually looking into right now. We're sending it to a company to have them actually quantify the octane number.
And the question, I think the process you are making, that butane now, the source of butane now will be a problem. You have from the wood you can have one of the raw material. But you still have to add the butanol to make the C9.
That's correct.
And where is the C4 compound, the butanol come from?
What's the actual industrial source
of butanol? And if you can make it from natural source, it will be very green, but where is that?
At this particular juncture, it is not particularly green. You are correct.
Okay, thank you. Appreciate it.
Really a dream project, I would say. And I'm sure, Dow Chemical has worked, Cargill has worked, done a lot of work on this. Still, they're not able to match the price of the petroleum. It's quite cheap.
No. It cannot match the price of petroleum. You are correct.
Correct, right. So that's not able to go. Only thing always I wonder, that from where we'll get so much hydrogen or hydrogenation?
Well, if JCAP's doing its job, then we're doing water splitting, and we're able to produce hydrogen. But at this particular juncture, I mean, what can you do?
Water splitting is not going to be cheap.
If JCAP's doing its job, it's cheap, but it will never be.
Right. As on today, it is quite expensive.
It is not as bad as helium, but at least we can generate hydrogen. Correct.
Right. And I'm sure, this is also generate huge amount of side product.
We don't have much.
Ultimately,
The generation of the hydrogen or the actual?
Hydrogen or hydrocarbon, whatever you say.
I mean, if you're doing hydrogen, then hopefully you're working, where sort of optimally you would be near an integrated IGCC plant, right? So they're taking CO and then you can spill out some of the hydrogen. You're still making CO2 in that particular instance.
Ultimately, that will be the choice, but we have to look up into all the aspects. Ultimately, how green it is. That's what my comment. I'm not asking a question.
Thank you, sir.
Because neither you have the answer nor I have the answer.
Anybody else? Okay.
Thank you.